Hello everybody. Today I'm going to present my wireless communication project on OFDM system where I've done a performance analysis on the synchronization methods and the PAPR reduction methods. The topics that we are going to cover today is Introduction to OFDM, why OFDM is important, the principle of the OFDM system, water filling algorithm, BER analysis, carrier frequency offset, symbol time offset, and peak to average power ratio reduction methods. So, what is OFDM? OFDM is a water filling algorithm is an algorithm that is used to analogously allocate data bits and power in an OFDM system. It is important because bandwidth should be effectively utilized and also to improve the throughput of the system. In OFDM, the water filling algorithm is used to vary the data rate and BER. This method does increase the complexity of the design because feedback is involved. Here we see the simulation output of the water filling algorithm, where we can see that based on the noise to carrier ratio, the amount of power allocated is higher. The next topic we move to is the bit error rate for different channel conditions. The bit error means errors found in bits during the communication process. BER is an important scale because it goes it is it is compared against different techniques that are used to implement and modify the OFDM system. It does help to use the most effective modulation method so as to reduce the BER. Signal to noise ratio is the ratio of energy per bit to 1 Hz of bandwidth. The paper includes BER analysis for which we will see the outputs now. In this in this slide we see QPSK modulation output comparison for guard length is 0 and guard length is 16. Here we can clearly see that for a signal to noise ratio of 10 dB, when the guard length is 0, it is less it is higher than 10 power minus 2, but whereas when the guard length is kept as 16, it is lesser than 10 power minus 2. The next slide we see a comparison of the QPSK and 16 QAM modulation, where again for a 10 dB SNR, clearly we can see that the BER is reduced. Also, it should be noticed that the AWGN is more in line with the simulation or theoretically calculated graph than the Rayleigh fading. That is because the Rayleigh fading is synonymous to real world scenario where there is multipath fading, whereas AWGN is more similar to theoretical consideration where only white noise is considered. Now we move on to the next topic, that is carrier frequency offset. What is carrier frequency offset? Carrier frequency offset is the difference that is observed between the actual frequency output and the nominal frequency. It is known as the frequency offset. OFDM system is a victim of frequency offset due to the presence of local oscillators in the transmitter and receiver. This results in the frequency shift. The repercussion of such a shift in frequency is felt in the performance degradation and large bit error rate. When demodulating something like a symbol synchronizer, the offset is also observed due to a Doppler frequency shift. This gives rise to a need to understand the frequency offset better and also to understand the techniques to estimate the offset. In case of OFDM, the subcarriers with higher frequency are more prone to to carrier frequency offset than the ones with lesser frequency. The integer frequency offset increases the BER, resulting in degradation of the performance. Here we see some of the estimation techniques that have been discussed in detail in the project. That is, the fractional frequency offset estimation techniques are cyclic prefix, where it is used exclusively for fractional frequency offset, and the Moose method, the disadvantage of which is that it has a higher mean square error, but it is a lot better than the cyclic prefix. The Klassen method uses the concept of training symbols, and it adds additional symbols to track the CFO. Here in the screen, in the slide, we see the output comparison, simulation output comparison for the three CFO estimation techniques that were discussed in the previous slide. Multi-carrier system that has gained its importance because of its ability to reduce failure rate, fading effects, and intersymbol interference that a single carrier system suffer from. Orthogonality of the subcarriers is the key element that makes it so sought after because it ensures that the subcarriers are harmonics. As a result, when these subcarriers add up, they do not cause interference. It helps achieve a high bit rate, immunity to multipath spectral efficiency, and in this project we will further see the performance analysis with respect to BER and effect of offset and PAPR reduction. So again, why is it so important to study the OFDM system? Because of high data rate demand, it means we need to use multiple carriers, which means we need larger bandwidth. OFDM is based on the principle that the subchannels must be orthogonal so that the numerous subcarrier signals can be transmitted without interference in a tight space of frequency. OFDM is very effective for communication over channels with frequency selective fading, that is, different frequency components of the signal experience different fading. It is very difficult to handle frequency selective fading in the receiver, in which case design of the receiver is hugely complex. Instead of trying to mitigate the frequency selective fading as a whole, OFDM mitigates the problem by converting the entire frequency into a simple fading channel. The other advantage of OFDM system is that every subchannel can use modulation, any of the modulation techniques like QAM, QPSK, AWGN, and so on. OFDM is different from other frequency division multiplexing because of the need for orthogonality. It also increases spectral efficiency and reduces intercarrier interference. So, what are the components that make an OFDM system? The main components are the modulation demodulation unit in itself, guard bands, IFFT, that is inverse fast Fourier transform blocks, and cyclic prefix. So, what happens in the modulation and demodulation OF, OFDM system? So, modulation in the modulation system, as we can see here in the block diagram, the input data is first converted to n parallel data with the help of serial to parallel converters, as we can see in this block diagram. The parallel data is then modulated with the help of n carrier frequencies. These subcarrier frequencies are orthogonal to each other, and during demodulation, the modulated passband that has been created during modulation is reconverted to baseband signals using low pass filter to obtain subcarriers. Now, the next part in the OFDM system is cyclic prefix. So, what is cyclic prefix? Let us understand that. Now, let us consider a non-ideal channel that causes delay dispersion. Delay dispersion comes across as symbol interference, and each subcarrier channel overlaps. It causes intercarrier interference due to non-orthogonality. So cyclic prefix is used. So what in a cyclic prefix, the last sample of OFDM symbol is copied to front of the next symbol. It helps add cyclic prefix because extension of the OFDM symbol time period happens, which in turn helps to decode even a late appearing signal. Now, what are guard bands and why do we need them? Guard bands Guard bands are needed to overcome the issue of adjacent channel interference. Again, this happens when there is a delay at the receiver while new set of data starts coming in through the transmitter. By extending the symbol period, data becomes corrupted as the data overlaps. Hence, there is a need for guard intervals that implements padded zeros, that is, zeros are padded at the end of every symbol, or cyclic prefix or the cyclic suffix method. One of these three methods are used as guard bands.